So the goal in this video is for us to begin to understand how to use deductive reasoning. Basically, we have to have a reason for everything we say. And in Chapter 2, these are going to be the reasons we're going to be using. So first of all, we have segment addition. Now, the way you recognize segment addition is it's two segments make a big segment. So two segments make a big segment. When you look at the picture, I'm adding AB and BC to get AC. So two segments make a big segment. Angle addition, same idea but with angles. Two angles make a big angle. ABD, the top angle, plus the small angle, make the big angle. Angle addition postulate and segment addition postulate. Those are postulates we use to add segments and add angles. Addition property of equality. This is what we do in algebra when we add 3 to both sides of an equation or subtract 10 from both sides of an equation. But in geometry, we're usually using segments or angles, and it looks different. It's kind of confusing because it looks so different. But here's what I'm trying to get you to understand. That like when we add 10 to both sides, we're adding the same thing to both sides. See here how we added CD and DE to both sides? CD and DE are equal. We're really adding the same thing to both sides. Doesn't look like it because they're different letters, but they're the same length. They're the same number. I'm adding the same number to both sides. Another example, subtraction property of equality, same idea. CD and DE are equal, so I'm subtracting the same thing from both sides. Okay, look at these carefully and make sure you recognize it. And notice how there are 4 segments in both cases, and we could do this with angles too. Don't confuse this with angle addition. Angle addition is 2 segments make a big segment. This is, I'm adding the same thing to both sides. Even though those things don't look the same, they're equal, so I am adding the same thing to both sides. So notice that there's no segment subtraction. It does not exist. We don't need it. That's why it doesn't exist. We don't add things we don't need when we prove in proofs. We try to keep the reasons as small as possible. Division property of equality, that's when I divide both sides by the same number. Multiplication property of equality, that's when I multiply both sides of the equation by the same number. Substitution, probably one of the most common reasons in geometry. When you run to one of these proofs on state tests, probably a good part of the time, substitution is going to be the reason. Substitution is when I plug something equal in another spot. So we've got AB equal to EF. That means I could replace AB with EF. So I'm going in this statement and replacing AB with EF because AB equals EF. They're the same thing. So when I replace AB with EF, I get EF equals BC plus CD. Substitution can look a lot different in different situations, but it's the same idea. I'm plugging something equivalent in another spot because they're equal things. Reflexive property of equality. The reflexive property is that anything's equal to itself or congruent to itself. Seems like a silly thing because it's kind of obvious. It ought to be equal or congruent to itself, right? But we use this in proof to get a segment in our proof that we need in certain situations. You won't use this so much in Chapter 2, but later on when we prove triangles congruent, we use it a lot, and it'll make sense in that situation. But you do need to know what it is now. Reflexive property, anything's congruent to itself or equal to itself. The transitive property, I just don't use as a rule. I generally just use substitution. Technically, substitution is a property of equality. However, in my class, I'm perfectly okay if you substitute with congruence. I'm not going to make you take another step and say they're equal first. So, transitive property kind of looks like something you've seen before in the law of syllogism. AB is equal to BC, BC is equal to CD. So it's kind of like substitution. I could replace AB with BC, and right here I'll replace it, and I get AB equals CD. So we can use the transitive property with both equal and congruent segments or angles. But as a rule, I'm going to stick to substitution. So I'm just pointing out that this thing exists. We won't use it very much. The linear pair theorem. If two angles form a linear pair, then the two angles are supplementary. We use that a lot. So basically, if we have a situation where like angle 1 and 2, they make a line together, a linear pair, line being the root word, that means the two angles add to 180. They're supplementary. This is a reason we use. You need to know it. Definition of midpoint. Another really common reason. A point is the midpoint if and only if. Hey, notice that biconditional thing going on. This is a definition. A point, I need points here, not arrows. A point is the midpoint, so there's my midpoint. If and only if it divides the line into two congruent segments. Now notice that's a biconditional. We could turn that around and say, hey, if a point divides a segment into two congruent segments, then it's a midpoint. And we could use the contrapositive and the inverse too. Generally, we use the inverse and converse with biconditionals and definitions most of the time. Definition of angle bisector. Again, there's that if and only if. Every definition can be a biconditional, a true biconditional. So a ray bisects an angle. It cuts it into two equal parts, so there's angle 1 and 2. And if this is ray AB that bisects that angle, then angle 1 would be congruent to angle 2. So that's a biconditional. We can turn it around and use the converse. If a ray divides an angle into two congruent angles, then the ray is a bisector of the angle. Definition segment bisector. Notice the conclusion here that it's a midpoint. So the definition states that it's the midpoint. A line is a bisector of a segment if and only if it passes through the midpoint of the segment. So if I use this in a reason, what I'll be concluding is that a point is the midpoint. It seems strange, but that's the conclusion. But as it's a converse, we could say, hey, if a point is a midpoint and that line passes through it, then it's a bisector of the segment. Now, it could be a line, it could be a ray, it could be a segment that bisects another segment. Definition of right angle. An angle is a right angle if and only if it has a measure of 90. We know that one. Definition of supplementary angles. Two angles are supplementary if and only if their measures add to 180. So we could turn that around. If they add to 180, then they're supplementary. Definition of complementary angles. Two angles are complementary if and only if their sum is 90. So if their sum is 90, then they're complementary. That's the converse. So there are a lot of reasons here. This is the last page, though. Congruent supplements theorem is not one we use very often, but basically it says that if two angles are supplements of congruent angles, so imagine, let me put a number in here. If I had 120 and 60, 120 and 60, do you see how 120 and 120 are supplements of angles that are both 60? Now, it's obvious with numbers, but when I put an angle in there and I go angle 1 and angle 2 are supplementary, angle 3 and angle 2 are supplementary. Well, since 2 is the same angle, like they're both 60 degrees, angle 2 is in both cases, that means 1 and 3 would have to be congruent. So we'd know that angle 1 would be congruent to angle 3. That's what the theorem's saying. It's not something we use that often, but when you put in numbers, it's much more obvious. That's the problem. Congruent complements theorem is the same idea. If I had a 60 and a 30 and another angle, different angle that was 60 and 30, but see these two are the same angle, and I know that the 60s have to be congruent. So if angle 1 was complementary to angle 2, and angle 3 was complementary to angle 2, then that would mean that angle 1 was congruent to angle 3. The right angle congruence theorem. Again, this one seems kind of silly, but it actually saves us a step or two. It's nice to have sometimes. All right angles are congruent to one another. It's true. Now, in the very last section, there are some theorems that come up, and we'll just mention them. Vertical angle theorem. We've talked about vertical angles. Vertical angles are congruent. The theorem says they're congruent, not the definition. So you can, for a reason, it'll be vertical angle theorem, or vertical angles are congruent. The common segments theorem, I did that out of order, but the idea is if AB and CD are congruent, then when I look at AC and BD, since AC and BD both contain that segment BC, then they would have to be congruent. So just think of the numbers here. Let me make up some numbers. Let's say this was 5, and this was 10, and this was 5. What I would be saying is that 15 is equal to 15. If two congruent angles are supplementary, so they're congruent, so this one and this one are congruent. They're supplementary, so they add to 180, and they're congruent, so they must both be 90 degrees. 90 plus 90 is 180. And this last one here, we'll just mention it. Definition of perpendicular lines. Perpendicular means lines that meet at a right angle. So if this was AB and AC, they are perpendicular because they meet at a right angle. Two lines are perpendicular if and only if they meet at a right angle. Again, it's if and only if. That means it's a biconditional. So I could say if they meet at a right angle, then they're perpendicular. In deductive reasoning, you have to have a reason for everything you state. So the way it works in a two-column proof is on the left side you have statements. So these are the statements. And on the right side you have reasons. So sometimes we have to be able to recognize things like angle 1 and 2. Angle 1 and 2 are formed by intersecting lines. They're vertical angles. So recognizing their vertical angles, why are two angles congruent? It's not the definition of vertical angles. That only tells you what they are. What it is the vertical angle theorem. That is one of the reasons on that list we just went over. Notice how I'm using the angle symbol for angle to make this shorter, and I'm shortening the words to make them easier to write. We typically do that. So as we look for reasons, we're looking for a hypothesis that two angles are supplementary and that there's a conclusion that goes along with that. Well, if I look at angle 1 and 3, you see how together they make a straight line? They're a linear pair. And the linear pair theorem says that if two angles make a linear pair, then they're supplementary. Notice what I just said. I concluded that they were supplementary, and that's what we've stated. I need a conclusion that they're supplementary, which is why linear pair theorem worked. Here I need a conclusion that two angles add to 180 degrees. Well, in proofs, usually the next reason, not always, but often, the next reason comes from the reason before it, or it always comes from above, or possibly the diagram. But we know that they're supplementary. That tells us they add to 180. So we need a reason for, if two angles are supplementary, then they add to 180 degrees. And that is the definition of supplementary angles. Number 3, angle 5 is congruent to angle 6. Angle 6 is congruent to angle 7. Given is what we know. This is what we know to be true. Well, if you look at this, they're both congruent to angle 6. So what I could do is I could plug in angle 5 for angle 6. That's called substitution. I could now state that angle 5 is congruent to angle 7 by substitution. More given. The measure of 5 is equal to the measure of 6. The measure of 7 is equal to the measure of 8. So this is like in an equation when we say x plus 3 equals 10, and we do the same thing to both sides, like we subtract 3, or if we had x minus 7 equals 14, we could add 7 to both sides. We're adding the same thing to both sides. So right here, 7 and 8 are equal. They're the same number, just like over on the right, we added 7 to both sides. So what we're doing is adding the same thing to both sides. That's the addition property of equality. Now, a lot of students get confused with addition property of equality, angle addition, and segment addition. Remember, segment addition is 2 segments make a big segment. Angle addition is 2 angles make a big angle. That is not what's going on right here. We don't have 2 angles equal a big angle. Number 5, we're given that B is the midpoint of AC. Well, we must be able to state something because it's a midpoint. And in order to state something, we need to know what a midpoint is, which means we need a definition. So our reason is going to be the definition of midpoint. So in if-then form, if a point is the midpoint of a segment, it divides the segment into 2 equal parts. So if B is the midpoint of AC, then AC would be equal to BC. You could also say that AC was congruent to BC. Notice the difference. If we don't put a bar, they're numbers. We put a bar, they're shapes. Shapes are congruent, numbers are equal. This is an or, either one. L bisects AC at B, so we must be able to state something. L is a line, and it's bisecting a segment, so that's going to be the definition of segment bisector. Now, it'd be easy to make a mistake here. You need to look at the definition of segment bisector. If a line bisects an angle, then it passes through the midpoint. So this is B is the midpoint of AC. And that's the definition of the segment bisector. All right, we're given that AB equals BC. AB equals BC. So if this is the converse of what we did above in number 5. Above in 5, we said if B is the midpoint, then 2 segments are congruent or equal. We're going to turn that around and say if 2 segments are equal, then B is the midpoint. So this is again the definition of midpoint. And what does that say? B is the midpoint. Number 8, angle 1 is congruent to angle 2, or their measures are equal. Well, those are vertical angles. That's not definition of vertical angles. The definition only tells you what they are. This is the vertical angle theorem. The vertical angle theorem says that vertical angles are congruent. Number 9, look at that. It's 2 segments, AB and BC, make a big segment. So that is the segment addition postulate. Number 10, 2 angles make a big angle. That is the angle addition postulate. Angle 1 and 2 together make AGC. GB bisects angle AGC, so that means that we have two equal angles, and that's what we're going to state. That would be angle 1 is congruent to angle 2. And why do we know that? Because we know what a bisector is. In order to know what it is, we needed a definition. This is the definition of angle bisector. Number 12, EGF, that angle, and angle FGB, EGF, and angle FGB are supplementary. Well, look at that. Together they make a linear pair. That is the linear pair theorem. Linear pair theorem. Used together they make a straight line. Well, we know they're supplementary. What does that mean? And how do we know it? We know it because we have a definition. We know they add to 180 because they're supplementary. That's what the definition of supplementary angles says. If two angles are supplementary, then they add to 180. The measure of 3 equals the measure of 4. If I look at angle 3 and 4, and if they are congruent over there, that means that we have a bisector. GE is the bisector. GE, starting at G and heading towards E, is the bisector. And we know that because if a ray cuts an angle into two equal parts, then it's a bisector. Number 14, two angles make a big angle. Angle EGD and angle DGC. So those two angles here make that big angle EGC. So that is the angle addition postulate. Two angles make a big angle. Last page here, hang in there. Try to recognize the reasons. The measure of 1 equals the measure of 3. And the measure of 4 equals the measure of 2. Those are special angles you need to recognize. They're formed by intersecting lines. That is the vertical angle theorem, which just says vertical angles are congruent. Now, this isn't real obvious the way it's written, but if I took this and wrote it underneath, the measure of angle 2 equals the measure of angle 4, just writing it underneath, see how they added those two and added those two, and how angle 2 and 4 are equal to each other? They're adding the same thing to both sides. That is the addition property of equality. Now, you might be tempted to look at this and say, hey, angle addition. But wait a sec, angle addition is two angles make a big angle. That is not what is going on here. This is not two angles make a big angle. So with addition property of equality, we usually have four pieces here, and that's a way to recognize it. And they could be angles or segments, either one. Number 16, we're given that FG equals GC. So this one, let's change colors. That one is equal to that one. Well, what does that tell you? It tells you something about G. If a point divides a segment into two equal parts, then it's a midpoint. So G is the midpoint of FC. And that's the definition of a midpoint. Number 17, angle FGD, that, is congruent to AGC, that's that. Oh, again, those are vertical angles. They're formed by intersecting lines, so they're congruent by the vertical angle theorem, which states that vertical angles are congruent. Number 18, G is the midpoint of EB. So EB, so that would be this and this. If G is the midpoint of EB, then we know that this segment is congruent to this segment. That would be EG is congruent to or equal to GB. So EG is equal to GB, or you can state they're congruent. Then you put a bar over it. And that's the definition of midpoint. Number 19, two segments make a big segment. That's segment addition postulate. And the last one, number 20. So we have a bisector. DA is a bisector. It bisects FC, bisects the segment at G. Well, the definition of segment bisector says a line is a bisector if it passes through the midpoint. Notice the conclusion. It passes through the midpoint. So we can conclude that G is the midpoint of FC. And that's the definition of segment bisector. Now, you might be tempted to say definition of midpoint because we're concluding it's a midpoint. But that's not it, because we're using the given. And the given says that line DA bisects FC. And the definition of a segment bisector says if it's a bisector, then conclusion, it passes through the midpoint. Well, we have G, a midpoint. What do we know about a midpoint? If a point is a midpoint, if then it divides a segment into two equal parts. This one is definition of midpoint. So what you need to do is find a reason that concludes what you're stating. So look through your reasons as you do these questions and look for a reason that concludes what your statement says. Take some practice.